Discuss how Snell's law is derived. Snell's law is generally used when studying refraction of light, and Snell's law states, over here as said, that for light traveling from one medium to another, the ratio of the sine of the incident angle to the sine of the refracted angle is a constant. Over here, light is traveling from point A to point B, and as it traverses from medium A to medium B, as it goes from A to B, it refracts at this point over here, and theta I over here is the incident angle, and theta R over here is our refracted angle. So mathematically, you would say that the sine of theta of I over the sine of theta of R is this constant over here. And what is actually this constant? Well, n sub b represents the absolute refractive index of medium B, and n sub a represents the refractive index of the medium A. Well, what is mu BA then? This represents the relative refractive index of medium B with respect to medium A. Now let's go and do the derivation. Okay, for the derivation, we use the concept of Fermat's principle. What is Fermat's principle? Well, Fermat's principle states that light travels from one point to another, traversing the least distance in the least possible time. So, this is Fermat's principle, and we use this concept over here as we do the derivation. As we proceed with our derivation, we first take the time as light takes to traverse from point A to the point of intersection of the light ray and the medium separating medium A and medium B, which is this blue line over here. Let's consider that time to be t1, and the time that it takes from going from this point to point B, let that be time t2. So mathematically, you would say that t1 would be d1 over the velocity of light in medium A, and d1 represents this distance over here. And similarly, you would say that t2 would be d2 over v2, and d2 is this yellow distance over here. Now, what is actually d1? d1 can also be said to be the hypotenuse of this triangle over here. See, where the perpendicular is h and the base being this x, this sky blue line over here. So you could write d1 as the square root of h squared plus x squared over v1. This is t1, and you can also write t2 to be the hypotenuse of this triangle over here, a minus x being the base and y being the height. And you could write this down as y squared plus a minus x whole squared over v2. Okay, now if these are the times, Fermat's principle would say that the summation of these two times, t1 and t2, should be as minimum as possible. See, for that to take place, you would say that the derivative of t1 plus t2 with respect to x over here would be the least as possible, right? So you would say that d dx of t1 plus t2 should be 0. Now, if this is 0, we could do further calculations and say that t1 is the square root of h squared plus x squared, and v1 over here, and the rest is y squared plus a minus x whole squared over v2. All right. Now, if you take the derivatives of these two things, these two terms, you would end up with something kind of like this. Right. This is the mathematical derivative, and if we set this equal to 0, as we said over here, through Fermat's principle, you would get that this is basically x over v1 times 1 over h squared plus x squared minus a minus x over v2 times 1 over this over here. Right. Let this be our first equation. Now, if we want to brush up our trigonometric concepts, our base for trigonometry, you would notice that this theta 1 over here can be written down as x over d1. Sine of theta 1 from the given image would be x over d1. X over d1. And we also know that sine over theta 2, if we look at this triangle over here, sine of theta 2 would be a minus x over d2, right? And then we can also write that d1 is basically the square root of h squared over plus x squared. So we could write that this is the square root of h squared plus x squared, and this is basically the square root of y squared plus a minus x whole squared, right? So we use these two concepts as equation 2 and equation 3. So if we use equation 2 and equation 3 in equation 1, we would get a certain result. So we use equation 2 and 3 in equation 1, and we get that this entire expression, x over the square root of h squared, x over the square root of h squared plus x squared, given over here, and a minus x over the square root of this entire thing over here, turns out to be sine of theta 1 and sine of theta 2 respectively. So we could write equation 1 as sine of theta 1 over v1 minus sine of theta 2 over v2 is equal to 0, as said in equation 1. If that is really the case, sine of theta 1 over v1 turns out to be sine of theta 2 over v2. We could also write this down as sine of theta 1 over sine of theta 2 is equal to v1 over v2. All right. Now, v1 and v2 represent the speed of light in medium A and medium B. This is in medium A, the speed of light in medium A, and that in medium B. Okay, so we also know that for light traversing in a particular medium, its speed v is basically c naught over n, where c naught is the speed of light in a vacuum and n represents the refractive index in that medium, the refractive index of that medium, index of the medium. If that really is the case, then using this as equation 4, we could write equation 4 as sine of theta 1 over sine of theta 2 to be c naught over NA and c naught over NB, where NA and N sub B represent the refractive indices of medium A and medium B. So we could cancel C naughts out and we are left with NB over NA. A. And you could also write n sub b over n sub a as this thing over here. Or you could also use nu over here. Therefore, we have that sine of theta 1 over sine of theta 2 is mu b over mu a. And this basically represents the relative refractive index of medium A medium B with respect to medium A. Well, this is the proof of Snell's law. In some books, you would also see this being written as n1 sine of theta 1 is equal to n2 sine of theta 2. This can also be represented by this, where n1 is basically the refractive index of medium 1, and n2 is the refractive index of medium 2, where light ends up finally at. Well, that's all.